Hey everyone, welcome to another episode of RoboPapers. I'm here with Yanjiang and Jianke, who are going to tell us about VLM4VLA, and excited to hear more about it. Could you guys introduce yourselves to start out with?
Yeah. Hi, Chris and Jeffrey. Thank you for having us on the podcast. I'm Yanjiang, fourth year PhD in Tsinghua University, working on robot manipulations. I'm very excited to be on the podcast today.
Yeah, hello everyone. My name is Jianke Zhang. I'm a second-year PhD student at Tsinghua University. And I am the first author of this paper, VLM4VLA. And in the later of this podcast, I will tell more about how we design and what's the conclusion we conclude from this paper.
Okay. Yeah, actually, this paper was done during Jianke's internship at Alibaba Quant Group. So yeah, basically I just discussed with Jianke. So in today's podcast, there's two parts. Yeah, I will talking about some motivations, basically some discussion period between I and Jianke, and then Jianke will go into the details of papers to share some key findings in the papers. Yeah. So the first part, I will talking about the motivations behind this systematically study. The main target of this paper is pretty simple. We want to build a generous robot manipulation policy. And for those audience who are not familiar with robotics, I will quickly introduce what is the generous robot policy. A generous robot policy basically maps the pixel observation and the language instructions to low-level robot actions. Ideally, you can input any observations and any instructions to the robot, and robot can always act properly according to your instructions. So if you look at the input and output of the policy, it actually maps very high dimensional input to some low dimensional actions. Since the pixel can be any images from the camera, and the instruction is just in the natural language form. Output is just the robot action space, typically a joint velocity, a joint position, or end effector pose, which is around 10-digit numbers. So we can see that it is a very high compression mapping problem. And when we built the generous robot manipulation policy, I think our robotics people are facing a very severe problem that robot data is very limited. And I feel that robot data is always much less than internet data. And this statement is true today, and I feel it can still hold in the future. So when we try to build this policy, we always start from some pre-trained models. Although these pre-trained models may not trained for the robotics domain, but we find them somewhat useful for robotics. So we will build a policy upon these models. So in the right side, I list some popular choices. For example, we can build a policy on the vision language models and transform it into vision language action models. And some people will learn some latent actions, and others people will leverage some video model-based policy, for example, by predicting the whole future videos and then learn some inverse dynamics models to output actions. And some computer vision people were using some flow models as the base model. They were tracking how the pixel in the image moves, and this movement can be very useful for robot manipulation.
Yeah. So just to make sure that I understand before we go on, let's say, so the idea is that, so you've got all of this, we want to train how to understand perceptual inputs and map it into something that you can use to predict actions. And so your argument here, or the argument here, it's not just yours, it's the general, everybody does this, is the idea that like you need to figure out, so you want to use web scale data to pre-train this. So you have these pre-trained models like a VLM, right? Is that roughly okay?
Since internet data have different forms, so there's also different types of pre-training objective. And people have already tried many different foundation models, and we want to show express is that at today, actually the state of the art policy is built on vision language model, right? if you look at the whole community, that the most impressive and most dexterous demos are all did with vision language model based VOA models. For example, in the below, I show some very challenging tasks on physical intelligence. They can using this robot arm to peel some orange and using some keys to open the lock. Yeah. So since there are so many choices of foundation models, we're curious why people always using vision language model as the base model. I feel this is a very fundamental question for all the robotics manipulation people. Yeah, if you ask robotics people why you're using vision language model as the base, actually I can get very different answers. Some people say that the vision language model already established some good alignment between the semantic and the visuals. So it is a very natural way to combine the visual input and the language input. And other people said maybe the vision language model can provide some good initializations and good representations inside vision language models. And other people said you can transfer some web scale knowledge from internet to robot. Yeah, but although they have different belief on why vision language model is useful for VOA, but the choice of vision language model is also very, I will say, very random. You can see policy built on llama-based large language model, or some Qwen-based, or some polygamma-based, or maybe some Ego 2 model-based. I just feel that the vision language model in the VOA domain is pretty random. And this is a little bit weird, because if you ask a large language model or vision language model researchers in academia, I think the default choice for them will be the latest Qwen model, because only built on Qwen model, they can fully leverage the advanced reasoning abilities of these large models. So when they do post-training, they can get the best result. But it seems that this is not true for the robotics domain. Robotics people just randomly pick a vision language model and then post-train this vision language model on their robotics data set. And this is particularly weird for us, at least. So yeah, actually, Jianke,
I have a question. I think it's really I mean, like, it's really like this summary from the systematics review sort of summarizes the different choices of how people build their VLAs with different choices of encoders, the base language model. And you mentioned that people use Qwen, the latest Qwen, which I totally agree. But I'm also curious to see that before making this argument, what is your thought of like thinking why? I mean, you listed out a few reasons why VLM should be the backbone of VLAs, but why it have to be the case, correct? I mean, like, how does putting everything to language helps with action? That's the I mean, I'm not saying that this is wrong. I'm saying this myself, but I'm just curious to hear from your thoughts why lifting everything to the language space helps with learning actions better, or why do we even need to use a VLM as a backbone in the first place?
Yeah, actually, I'm also not certain which backbone will be the right choice for learning generalist robot policy. But in my observation, at least at today, the state-of-art vision generalist policy is built on VLMs, right? Actually, Jianke and I also did a lot other studies, train a lot of other models. For example, we train some video prediction-based policy, and then we also train some VLM-based policy. And in our past feelings that the VLM-based VOA still works the best, especially when you try to do these dexterous tasks. Yeah, but I'm not sure whether it's true in the future, since recently there are also many models based on video generative models. Yeah, they're also very impressive. Yeah, but so this study is basically focused on the vision language model based VOA. In our previous feelings of training VOA, we feel that VOA model actually cannot leverage the full capabilities of VLMs. For example, there are many reasoning abilities inside VLMs, but the task in the robotics domain actually is quite straightforward. You just instruct a robot to do some daily tasks. which may not require any reasoning. And the second is that also we feel there is some misalignment between VLM and the training and the VLA learning. Even the whole capability of VLM is not sufficient for the VLA learning. Yeah, we all know there is a famous phenomenon or famous moment is that when Google first trained a vision language model RT2, they find the robot can approach the Taylor Swift picture, right? So that vision language model is very good at providing this semantic level information and tell you what this object exists in which patch of the image. But I feel that there's a lot of other things that are missing that is necessary for the robot. For example, the motion level representations, how you should approach the object, from which direction, for example, and how you should grasp the object. And this part, I feel this part is actually missing in the vision language pre-training. And another very important thing that when we post-train the VLM to VLAs, actually it's very hard to preserve semantic information inside the vision language models. And we design a lot of techniques to preserve this knowledge. For example, by co-training with web data or using some discrete tokens like the FAST paper did. And yeah, but even though with all these techniques, I feel we still cannot fully preserve the semantic knowledge inside the VLM. Yeah, that's some of our previous feelings when we train VLA models. Yeah, so yeah, next step. Let's go into the next part. Jianke will go into detail.
Okay, thanks, Yanjiang. Okay, here I am now give you a more detailed look into how and we design the experiments and walk through some of the key conclusions we draw from the results. So the first is the challenge we may encounter. I think the biggest obstacle to exploring the core question of what VLM is best for VLA is to ensure a fair comparison. We see dissatisfaction from all concerners of the community regarding current VLA performance benchmarks. This frustration stems from the fact that every part of the robotics experiment and validation pipeline involves a vast number of detailed tricks. Furthermore, every benchmark and indeed every in the real-world task has its own inherent biases. And when you combine all these factors, the true differences brought from the VLA back architecture and the VLM backbone itself can be masked or completely hidden. So, for example, in challenge 1, different models use different architectures, different training data, and different evaluation benchmarks. This makes it incredibly difficult to compare results and know if the performance gain comes from a better VLM or from other factors in training setup. So to get a clear signal, we needed to establish a controlled environment where we could isolate the VLM's contribution. So in this part, we will use a unified benchmark, unified codebase, and a unified data process, and get all the tricks a uniform part. Also showing in challenge 2, we need to identify the core VLM capabilities. What specific properties of a VLM is its size, its architecture, the kind of data it was trained on, are most critical for VLA tasks. Our goal was to create a framework that could help us probe these properties systematically and fairly. So we discuss about why we take this VLA architecture design. We opted for a minimalist design. Our goal was to let the VLM do a heavy lifting, so we built a very simple bridge between the VLM's understanding and the robot action. We wanted to minimize the influence of complex policy head. So our design has the 3 core principles. We use a simple action query with a few learnable tokens to extract action-relevant features from the VLM. And the action itself is predicted by a simple MLP head with L1 or L2 loss. This avoids the complexity and randomness of other action representations such as diffusion or flow meshing, since this kind of diffusion can incorporate a random noise from each rollout. So we need to test more times during evaluation. And thirdly, a very important part is the prompt design. The very prompt for an input sequence. We found that the specific order in which you switch together the instruction, the image features, and other inputs can affect the model's performance. This is a critical detail that is often overlooked, with many existing models failing to clearly document their import structure, adding yet another layer of inconsistency to the comparison. For example, in the preliminary tests, by freezing the VLM and using different prompt design, we saw performance jump from 18th to the 25% on the simpler pick and place tasks compared to more complex setups. This means that controlling the prompt consistent across all models is important for a fair comparison. We carefully designed our prompts to align with how the VLM was originally pre-trained. This allows us to leverage its existing language understanding without needing to teach it entirely new ways of thinking. Like as shown in the first row in the tab, first row in the aligned. This is the prompt used for Qianwen series model, which is strictly aligned with its instruction following format. We found that this difference can bring a suitable degradation to final performance as shown in table between the aligned one and the not aligned one. Okay, so
I have a question about this. Sorry, just a quick question. Have you guys also tested just using random text and not with any specific meaning, just having like long random text of long sequence? Because I mean, like, is the language semantics that's actually causing the performance gain, or is it the length, or is it like, because after all you're doing full fine tuning, so you're not doing in context learning like what VLMs are able to do when they train with huge amount of data. In this case, I guess you're just fine tuning. Yeah, so I just
that's an interesting point. Maybe we can refer to the bottom interesting observation part. We see that if we just input the pick the cube, like we get 18% access rate. And if we apparently let the model to locate the position of the block, like we add a in-context learning or some bias into the instruction, we can get a higher success rate on this task. So I think there should be some kind of the instruction format that can leverage the inherent VLM. And we don't experiment on the random instruction format, but I think a consistent instruction like aligned with the pre-training is the best choice.
I see. Okay.
So what did your pre-training data look like then? So your pre-training data looked like the latter one? Looked like...
pick up the cube.
Yeah.
The aligned one. The aligned one is the fully consistent with the Qianwen pre-train, Qianwen instruction following format.
Okay, sounds good.
Yeah.
Okay.
The next part is the choice of VLMs. And we focused on models from the 1 to 10 billion parameter range. This represents a practical trade-off between model capability and the computational efficiency needed for robotics research. And we try to fine-tune VLMs with auxiliary VQA tasks and use them as the VLM backbone. Like shown in the part B, I need to clarify a very difference between this paradigm with the co-training paradigm. In this paradigm, we first post-training the VLM and then take use of the post-trained VLM as a backbone of VLA. So we did not incorporate the co-training paradigm. And thirdly, we want to understand the bottleneck of current VLA so that we partially freeze the VLM backbone. So the next part is about training and evaluation. As I mentioned above, to maintain the training and evaluation consistent across all models is very important for the fairness and reproducibility. So we ensured a consistent setup for all experiments, like a single non-moving camera view, the same image resolution, no perceptive feedback, and the same loss function. We evaluated our models on multiple simulation benchmarks, and including the below Kelvin, simpler, and liberal. Because simulation provides a controlled environment, unlike real-world tests where many variables are uncontrollable. Also, we found that action chunk and training setups is a crucial factor that affects model's performance. So we test multiple times across the training steps with different action chunks to further avoid staticity of training. To some extent, this consistency allows us to confidently attribute performance difference to the VLMs themselves. So let's talk about the first experiment. So what did we find? We confirmed a significant gap exists between a VLM's capabilities on standard web data benchmarks like VQA and its performance on physical manipulation tasks. The left two table shows the different VLM for VLA backbones on the Kelvin, Simpler, and Liberal benchmarks. And the right table, we show a linear similarity between the VLM performance and the VLA performance. Now, this brings us to one of the most interesting findings of our study. If we look at the chart in the top right corner, we visualized the linear relationship between a VLM's general VQA capability and its final VLA performance across different simulation benchmarks. What we saw was fascinating. Only on the Kelvin benchmark did we see a somewhat positive correlation, meaning a better VLM tended to lead to a better VLA agent. On the other two benchmarks, there was no obvious relationship at all. A model's VQA score told us almost nothing about how it would perform on its robotics tasks. So what should we make of this observation? I wanted to discuss a few perspectives on this phenomenon. First, we must acknowledge that simulation benchmarks have their own distinct biases. Our results clearly show this. You cannot simply look at the performance on a single task or a single benchmark and draw a universal conclusion about a model's capability. The positive correlation on Kelvin might be because its long horizon multi-step nature aligns better with the high-level reasoning and that VQA tax measure. The other benchmarks might prioritize different skills. This reinforces the need for multi-benchmark evaluation. And second, while many people will tell about I did not experiment on the real-world task, and here I want to get a discussion. While a gap between simulation and the real world definitely exists, I believe the gap we have identified here between VLM capability and VLA performance is more universal one. It reflects a fundamental heterogeneity between language and action. Language is a symbolic and abstract, and action is a physical, continuous, and demands precise spatial geometric awareness. Our results in simulation reveal this mismatch, and I argue that this is a core challenge that will persist even when we move to the real robots.
I have a question. So I think this makes a lot of sense, right? So like obviously evaluation in robotics today in simulation is just not perfect. But I have a question, which is that have you guys tested this correlation in like out of distribution scenario? Because it seems like it seems to make more sense to me for OOD context for you to actually see a correlation with a stronger VLM that will lead to a better VLA.
Yeah, actually, in these three benchmarks, there's kind of OD, but maybe that's not what actually many people's concerned the OD fact. Like in Kelvin, I test on the ABC to D tests. So in D, the background of the scene is totally changed. Like in ABC, we are trained on the black, white, yellow, but in the D, we test on the another pink like background. And in Simpler, there's also this very big real to sim visual gap. Like we trained on the real world data set, but we are evaluating in the simulation. So the visual gap is very big. And liberal, I think that's quite a not very OOD simulation benchmark.
But the funny thing is that it looks like strong correlation where there's OOD, which is Kelvin. I guess Kelvin is like you did the ABC and test on D kind of thing. So you see a strong correlation. And then as the thing gets more and more, in distribution, the strength of the VLM disappears. So maybe the use case of VLM will be is meant for like improving OOD for VLAs. Like, will you be able to draw that conclusion based on evaluating on these 3 benchmarks, or do you think that we should look at more like Liber Pro or look at Colosseum, look at this kind of benchmark that just studies out of distribution shift? Yeah.
Yeah, I think we should focus on the OD because my faith in the VLM is that the VLM based VLA can have a good semantic generalization. What semantics means is that I think our VLA should have the ability to handle the unseen objects and unseen scenes or unseen background. And actually, I think nowadays recent simulation benchmarks is lack of it. Like Kelvin, it just has a zero gap, and also Simpler is also a zero gap simulation benchmark. Like this is also actually these benchmarks lack of kind of semantic OD tests. Yeah.
Even the visualization, even the variation in Calvin is pretty minimal, I would say. Like, I guess like Jianke was saying, you could try on a totally different, like held out simulator, like Colosseum or RL Bench, whatever you want. And that would be potentially interesting, but maybe we'd let the, what do you think would happen? Do you think none of them would succeed at all, or?
Yeah, I can say something about these new benchmarks. I feel that today's robotic data set coverage is still not dense enough. So if you try brand new skills, you definitely failed. And what can generalize in my previous observation is that you can generalize on this pick place style motions, right? This you can only generalize on this same category of task. You can't just put it to a very novel task. Yeah. So yeah, but these 3 benchmarks actually are most popular and widely used in today's paper. But actually, they are very bad at this testing this semantic level generalization, even for these pick and place motions. So yeah, I expected that when we try this model on OOD scenarios, VLM models can be better at to the same category but semantic different tasks, but still failed in this novel tasks, requires brand new skills.
Yeah, I think I agree on that. And then I think another thing that I also, I'm not sure whether it's related, but like another paper that I read recently about catastrophic forgetting of semantics as you go from a VLM to VLA. So imagine you try the same VQA or like VQA benchmark on your VLM, and then you try on the VLA side, you realize that it just went all the way down.
Yeah.
Right?
Yeah.
I mean, Momo it doesn't. Momo actually stays pretty high. But what I'm trying to say is that, like, do you think the ability to still retain semantics in a VLA matters towards, getting the performance up? And if that's the case, like, what is the best VLM to sort of support that? Yeah.
Yeah, I think it's very important to preserve this semantic generalization abilities when you try to transform a VLM to VLA. And yeah, so since we cannot fully preserve this generalization capabilities, maybe we just preserve a small portion of these abilities. So it doesn't matter what the original VLM is, because you're just using a little part of it. So which makes no matter what VLM you use after fine-tuning it on robotics, they will finally become similar. You are just using a small part of it. And yeah, just as I said in previous slides, I feel we do not using any reasoning capabilities of these VLMs. We are just using some very high-level semantic, patch-level semantic informations, which I think today's modern VLMs are very good at. So maybe you just random select a modern VLM is already enough for in today's paradigms, since you only use a little portion of this VLM capabilities.
Is that because our tasks are too easy, or is that because they're of the catastrophic forgetting, or like basically when you're fine tuning it, or is it a little bit of everything?
Yeah, I think we are not able to tackle too difficult tasks at the same time. So today, when we're training generous robot policy, I feel we are largely focused on some pick and place style motions or some variants of pick and place tasks, which requires very little reasoning abilities. And another problem is how you're preserving this semantic generalization knowledge inside VLM, which is, in my opinion, very hard. Yeah, even we try
even
very
with
hard.
co-training. Did you guys try?
Yeah, even with yeah, because the co-training scale is much smaller than the pre-training stage, and also we introduce a new modality, which is action modality, into the VLM, which may destroy some internal structures that pre-trained VLM is optimized to. So I feel, yeah, we just can. It's very hard to fully preserve the generalization, but we just preserve a little part of the VLM capability.
Did you notice any trends as far as the backbones or the VLM experts, the quantities of data or data mixtures that they were trained on? Were things from like the Quen family better than Gemma? Or what were your findings, or what are your impressions? I guess we can look at the numbers here.
You mean how the VLM pre-training data
right? Yeah. How does the VLM pre-training? And I'm particularly curious because we talked about this at the beginning. Like, how does the VLM? Do you have any ideas how the VLM pre-training impacts the results?
Actually, I think I don't know what kind of data Polygamma use, but I know what kind of Qianwen use. And I think the main difference between Qianwen and the Cosmos, the lowest one. The main difference between these two models is that Cosmos is a 2D grounding only data pre-trained. Like this model can only get some big box or locate some objects, but Qianwen is for the general capability. And also Polygamma, I think, is also kinds of this kind of model that it is partially enhanced for specific tasks like 2D grounding, semantics mapping, or something like that. But it's not capable for the general use, like we can chat between the model and the human. Yeah. So I think from this perspective, all these models have kind of semantic between the language and vision. But Qianwen is better on the reasoning and language format. Like it can speak out a very long and human-like language. But for Cosmos and Polygamma, I think this capabilities is much less than Qianwen.
Yeah, so that's extremely interesting. Looking at the numbers that you got, or honestly, just from running the experiments, from your opinions, do you think that made a noticeable difference? Do you think that mattered how those things were trained? And when you then downstream tried to apply it to robotics, I guess. It's the answer is no. It's really hard to tease out a trend from these numbers, to be honest. So it may well be that like this is not like the robotics data just washes out all these choices, which would be an interesting finding, I guess. Is that what your opinion is?
I think also another problem is that it's harder for us to know what is the data that went into training the VLM backbone, right? Which is that.
That's fair.
I mean, think of it as this way: does Gemini robotics actually need the ER version, or is the ER version just the Gemini? Correct. Like why?
I don't know.
Does the data actually make a difference? It's hard to tell. Okay.
Yes.
Yeah. And also, Quen only released one checkpoint for these models, and you don't know how they choose the data mixture and how they training. They have different stage of training, and which makes the final result very complicated. For example, the Quen VL is built on Quen model. Quen is the language model, and then you need add some visual language data and then training with, I remember it's 3 or 4 stage of training. Actually, it's quite complicated pre-training process. And then you get final checkpoint and they release it to you. And it's very hard to do ablation study on the data mixture, I feel.
Yeah, but I guess maybe you guys know why is the actual stat. Because this paper is from Qianwen, right? I mean, obviously you don't have to share, but just curious. Yeah.
Okay, so maybe we can come to the next.
Yeah.
Okay, here, this part is my curious about what kind of VLM pre-training data can influence the VLA performance. So for my bias, I chose this kind of data type. You can take a look at it. And in this part, we try to evaluate how different VLM pre-training auxiliary tests influencing downstream VLA performance. And these 6 types we considered, including the pointing, spatial understanding, embodied understanding, and other general tasks like the Robo2 VLM. this is a question choice on the robotic things, and also the 2D grounding in the RoboBrain data. And also, this is a internal data for Qianwen Omni generation tasks. Like we add a DIT head on the Qianwen model, and it can handle both the language output and the image generation. So we incorporate these pre-trained VLMs to the VLA backbone. And in our experiment on Kelvin, we found that simply fine-tuning a VLM on a single specific embodied task does not really improve its end-to-end VLA performance. By the way, I have indeed recently received some discussions and questions regarding this part of experiment. I feel it is necessary to clarify here that this part of experiments were evaluated in a single simulation environment, Kelvin. It is certainly possible that the results could differ in other environments. We report these findings to present an observed phenomenon, and we find that this simply adding the VLM training tasks cannot get a better VLA performance. Yeah.
I have a question. So is it like you run multiple checkpoints by just iterating with different mixtures, or do you also do downsampling a certain one? So you basically you either add, for example, RoboPoint, or you don't add RoboPoint completely. Is that what this plot is trying to show?
What do you mean?
Like you basically retrain, you basically sort of redo the entire pre-train of VLM by incorporating.
Oh, no. I just post-train the VLM on the specific dataset.
Oh, so you post-train the specific dataset together with
Yeah.
Okay.
Yeah, actually, this is also a formal technique. Like in RoboPoint or Robo2 VLM, they also fine-tune the Qianwen series and evaluate on their benchmark. So
but
I do
you
the
did fine-tune
similar
it on
things.
this plus robot data to see how well, right? Or is it just on the robot data? Or sorry, just on this?
For the task except the VQA mix, I just fine-tune the Qianwen model on these specific tasks. And for the VQA mix, I mix all these kind of data and also the Qianwen post-training data. So we find that actually the VQA mix gets the best score. And this may reveal that the general capabilities of VLM is very important.
I see. So you did the post-training from the Q1 post-training mix, which is not open source. Okay.
Yeah.
Okay.
No, I did a post-training from the released open source Qianwen model.
Okay. No, but the data, is that are you using internal quants? Like, do they have an internal post-training data set, or they were just, okay, I understand. Okay, I get what I mean. Yeah.
For tasks except the VQA mix, we only use the open source dataset. Like Robo2 VLM is open sourced, and RoboPoint is also open sourced. For only the VQA mix, I mix the open source dataset with their internal dataset. Yeah.
Right.
I mean, you all started with quiz sonnet with Wentao in the days. Do you remember sonnet? Yeah.
So this result, I think, is not as what I think before I do this experiment. And I also recently saw a validation study on the co-training VLAs with VQA tasks. And these findings found that adding VQA co-training during the action fine-tuning phase significantly boosts VLA performance on out-of-distribution tasks. And I believe this finding is very reasonable, and importantly, it does not contradict to this observation. And in fact, it fits perfectly, I think. The co-training approach essentially works to preserve the VLM's intrinsic semantic alignment, preserve the VLM's while it's training the new robotics task. This preserved general knowledge is likely what helps with the OOD generalization. But in contrast, in our experiment, which was designed differently, we tried to enhance the VLM's capabilities before the action fine-tuning began. It's highly probable that this enhanced ability was then partially lost or washed out during the subsequent intense fine-tuning on action data, which is why we didn't see a performance boost in our setup. And of course, one could argue that the Kelvin benchmark isn't old enough to show the benefit. But personally, I think I don't believe that's a primary reason, and I think maybe this reveals some kind of fundamental flaw of current data.
So, okay, I have a question, which is that you take the open source checkpoint of Quen 2.5 3B model, and you did this experiment, correct? So I mean, I'm curious to hear that, because the release checkpoint is already incorporating data set, for example, Pixmo, which already have pointing. So how much of that actually helps, correct? Like, will it make sense to actually do this experiment in the pre-training stage rather than in the post-training of the VLM? Yeah.
Actually, I don't have enough resource to do this kind of ablation study.
Yeah, so that's my question, because I thought that experiment like this will be too expensive to do, but maybe you are in Alibaba and Quen, you can try to do this.
This kind of experiment is very expensive because you need to modify their pre-training, and pre-training is usually done with very, very large GPUs. Yeah.
Okay. So they didn't allow you to do that, Quen, Alibaba.
I can only post-train these release models.
That is a shame.
Yeah. Like on only 800.
Yeah, that's a shame, because you have much more insights you can do from the pre-training step. Yeah, but anyway, yeah, just.
So yeah, and here we come to the next freezing different parts of the model to see which modules are important for VLE fine-tuning. The results shows that the vision encoder is an important part across screen model or polygamma, and this led us to identify what we call the visual gap. We want to explain why vision modules within the VLM should be fine-tuned for VLE. Is there any deeper factors, and maybe we can find a way to compensate this gap, or even freeze the visual module during utilizing other techniques in the future. Let's come to the next PPT. So in this experiment, we first need to discuss about what the potential sources from this gap between the VLM capabilities and VLA performance originate from. The first and most obvious reason one might suspect is the domain gap between the simulation data environments we test in and the real-world web data the VLM is trained on. This is the factor 1. To investigate this, we use the simpler benchmark, which is the real-to-sim environment. For our training in simpler, we use the Bridge V2 dataset, which is a large-scale dataset collected in the real world. Now, if the real-to-sim gap were the primary cause of the problem, you should expect that when we fine-tune the model on this real-world Bridge V2 data, we wouldn't need to update the vision encoder. After all, the VLM was pre-trained on real images, and now it is being fine-tuned on real robot data. The domains should already be aligned. But however, in the tab you can see on the left, this is not what happens. Freezing the vision encoder even when training on this real-world dataset for the simpler environment still results in a massive performance drop. This result is a crucial piece of evidence. It strongly suggests that the simple real vs sim domain gap is not the core reason for the performance gap we are observing. There must be more fundamental factors at play. So in the next, let's come to the next. So here, we provide a hypothesis as a factor 2 that may cause the problem. Consider the visual features needed to answer the question like, what color is the apple? Are very different from the features needed to guide a robot arm to pick up the apple. The latter requires much more precise spatial and geometric sensing, also what we called information suitable for low-level control. So here we try to conduct an experiment to reveal whether the gap originates from the gap between these VQA targets and the VLA targets. More specifically, the gap between semantics understanding and low-level action control. We find a potential way to mitigate this. We found that if we fine-tune the VLM with action using QA format, such as the fast token used in PyFast, we can help compensate for this visual gap. As shown in the table, we conduct an experiment using different settings of fast token tuning and VLA tuning. The left part denotes freeze vision module during VLA training. In our previous experiments, we show that this should bring a big performance drop. The right part is unfreeze visual part for VLA training. which should bring a better performance. We compare whether using fast action token for VLM pre-training can benefit downstream VLA performance. So take a look at the results, specifically at the second and third rows of table. This is what it gets really interesting. The second row shows that if we fine-tune the VLM using fast token but keep the vision encoder frozen during the fine-tuning stage, we still need to unfreeze and train the vision encoder during the final VLA training to get good performance. But look at the third row. If during the initial VLM fine-tuning we unfreeze the vision encoder and let it train, something remarkable happens. We can then freeze the vision encoder during the final VLA training and still achieve strong performance. This contrast is extremely telling. It demonstrates that the gap between VLM and VLA may originate from the action information itself. The backbone vision module must be exposed to action-relevant information at some point to perform well on the VLA task. This directly validates our hypothesis for factor 2. The gap stems from the fundamental heterogeneity between the task of visual language understanding and the action control. And simply understanding what is in an image is a different visual problem than understanding how to interact with it. So this is our last experiment.
Yeah, this is really interesting. So I guess on that note, so if it needs to be exposed to vision information. There's a clear distribution mismatch between the VLM and the information. Do you have any, I guess, recommendation? Do you think that means is that I guess maybe a good sign for all these people now are working on video models? Do you think that you'd see the same pattern there because video models have more action incorporated in them, or what are your thoughts? I know this is outside the domain of the paper, this is speculation, but
this is a very interesting question, and maybe we can do some research on VLM4VLA or something like that.
Right,
and I think video model is much better at the action control, I think, because video give a better dynamics bias for the action, and VLM only gives a semantic alignment.
Makes sense. Do you think that do you think we're just pre-training VLMs or on the wrong images? Do you think there's some set of images that would be better for this, maybe? Clearly robotics data would, but that's...
I think actually this part of experiments, initially I want to provide a way to pre-train a much better VLM backbone for the VLA community. And actually in the experiment 2, using the VQA auxiliary task, in that part, I want to know what kind of specific tasks like embodied understanding or spatial understanding can enhance VLA performance. But actually, as the conclusion, I think only the simply adding some kind of VQA task on the robotics is not enough. And in this part, I think the most important part is that to incorporate the action-relevant data into the VLA pre-training. Like FAST is a kind of tokenization that tokenizes the action into the language token so that we can pre-train it in the VLM. And this indeed gets some effective results on the simpler benchmark.
That makes sense. So, okay, one more follow-up, and then I'll let Jeff ask any questions. But that makes that theory makes a lot of sense. But a couple slides ago, we saw the Cosmos one, which you said was bounding box prediction, right? And the image. So that to me seems closer to action prediction than just pure question answering. And yet that did worse. Is that because is that basically just a coincidence? And it's because Cosmos was also trained on less data or less diversity or something? Or do you think, basically, can you explain that to me? I guess is the question. What do you think is happening?
You mean the Cosmos predict the NVIDIA? Maybe that's a prediction model, I think, not a VLM.
There was the VLM backbone that you had in the a few slides back in the first results page that you said was doing. You said this one here, this one, Cosmos 2. You said that was doing bounding box prediction, right? Actually, I'm not familiar with that one.
Okay, so you mean that the pre-training data between the Qianwen and the Cosmos?
Yeah, so I guess so to rephrase the question, so like some of these models are trained on different mixes of question answering tasks. Some of the I thought you had said that this one was trained more on like bounding box or point prediction. So if the theory is that action information is important, that seems to me at least to be closer to action information, because it's like saying like this is the object I should grab. So if this is true, and if there's no other like confounding variables, model size is clearly one, like data size, then would I expect that to do better? Or do you think those confounding variables make it hard to draw the conclusion, et cetera? Does that question make sense? I'm sorry, it's a very kind of complex question or convoluted question, let's say.
Yeah, I feel that bounding box and this kind of traditional computer vision training objective is definitely closer to action, but not close enough.
Okay.
Because it provides you, for example, the object is located in which pixel of the images, but you still don't know how you should approach an object, from which direction you should approach an object, and which point you should grasp. I think bounding box only provides you at the patch level the rough spatial location of the object, but you still need some much more information in order to generate the action sequence. Yeah, it's definitely much closer, but not close enough, in my feeling.
Any
Yeah,
questions
actually,
oh, sorry.
I want to add some points that actually this kind of experiments, I think the action relevant information should be incorporated into the VLM is for some kind of foundation model company to do. Like they can incorporate all the big robot data and tokenize their action and formulate it as a big VQA data and pre-train their VLM into it. So that's when our robotics community take use of their VLMs, we can use of their pre-trained VLM on the very large robot action data and fine-tune on our action data so that we can do a very quick and get a more generalizable VLA.
I have a more philosophical question, which is that, think of it in this way, which is like today's VLA models are just like a black box, right? I mean, like you have no idea like how you prompt it. Like you can, for all you know, you just change a single letter and somehow the model starts to break. And that's bad because we are not able to do failure analysis. Whereas like model-based approach, which is like more modular, for example, for sure where something might fail. It might be the perception system might fail, the grasping system might fail, or somewhere might fail along that chain. So do you think that the way forward is for us to come up with a variable way to actually diagnose the VLM and then diagnose how, because of the data, because of architecture, and then be able to sort of diagnose the problem that's occurring and then informing our VLA model? How do we make the current status of black box of VLA become something that is more diagnostic, and we can sort of understand, why something is wrong? I mean, there's so much, like, for example, you say you try different prompts, right? Like I know people like from UPenn, I mean, like Tony, which he tries like 1,000 different prompts on Pi, and then you have different effects. So how do we sort of go about doing this? Or do we just, vibe check and use vibe to sort of have a sense? Yeah. Any thoughts on this?
Maybe I can say something first. Jianke, you can say later. I feel, in the context of vision language model, actually you are very difficult to know the result in advance. Maybe you can design some VQA problems. For example, if you want to grasp something, you can ask, can you draw the bounding box for that object? And if the model can draw the bounding box correctly, it can indicate the model has a larger chance to succeed in that tasks. This kind of high-level questions, you can design some high-level VQA questions, but I think it's still very difficult to fully predict the result without roll out it in the real world. This is very hard for vision language model, but for the video model, maybe you can look at the predicted video, which is much more straightforward. You can look whether the motion is correct or, that would be much easier, I think.
So should we look for a new version of this paper from you guys on video models?
Yeah, actually, I have an initial plan on video models. for vision language action model.
Yeah, I think it would be really nice is that instead of using the benchmark, like for example, using the benchmark that people have been using, which is basically about overfitting, like to come up with a few tasks that actually requires you to really look at this problem. So I'm just saying I don't have anything in mind concretely, but for example, a very simple problem would be your VLA actually know when to stop. I mean, I don't think it knows when to stop doing something.
Yeah, you don't know.
Like even Gemini uses a separate Gemini ER version to sort of look at the frames and determine when to terminate. And that's not like you have two separate models that's doing this rather than a single VLA model. So like a simple task like knowing where to stop can test, how much of that semantics has been, leveraged into the action prediction. I mean, what I'm trying to say is that maybe like if there's a follow-up, as what Chris mentioned, like maybe having like special tasks that actually requires, really dive deeper into this would be great, because then the task will give the example that, okay, you see, you can't solve this. And I mean, obviously, as you guys mentioned, the current benchmarks in robotics is not that, I would say, not that useful, but it's not there.
Yeah.
They're not
That's
perfect.
quite a problem. Actually, I think a potential of the current VLA is that actually in these kind of benchmarks, we are just fine-tuning the VLM to some kind of overfitting the benchmark dataset. But for the future, I think the VLA paradigm should be the VLM itself can spell out some kind of language. Like you can detect the success and stop the action, or do some subtask planning or something like that. And it can get all the models output in the interleaved format. So maybe we can come to the conclusion part.
Okay.
Okay, so our investigation led to three main takeaways. First, current off-the-shelf VLMs, despite their impressive performance on general VQA tasks, often lack specific abilities required for embodied VLA tasks. There is a missing piece. Also, we show that all three benchmarks for robotics has kind of bias, which requires models different capabilities. And second, we did not identify that a simple boost to the VLM via special understanding task can translate into better end-to-end VLA performance. Maybe co-training or other paradigm can bring different effects. But overall, this problem is more complex than we suspected previously. And the core issue as we see it is a visual gap, a fundamental mismatch between the visual understanding required for high-level language tasks and the fine-grained spatial geometric understanding needed for low-level robotic action control. And finally, we wanted to use a simple diagram to summarize our finding of the relationship between current VLM and the VLA models. We believe that at a high level, both VLM and VLA training require a fundamental alignment between vision and language. Their overall training objectives moved in the same general direction. This is why the pre-trained initialization for a VLM is so critical for VLA performance. You cannot just start from scratch. It provides an essential foundation. However, and this is a crucial point, we believe that during the later stages of training, their paths diverge. The post-training or fine-tuning that makes a VLM score higher on VQA benchmark is not aligned with the fine-tuning objective for a VLA. As the diagram shows, they begin to optimize for different things. This divergence is caused by the task heterogeneity we have been discussing. One path optimizes for high-level semantic understanding, while the other must optimize for low-level spatially precise action control. And this, we believe, is a fundamental reason why our simple attempts to strengthen the VLM's general capabilities did not directly translate into better VLA performance. We are pushing the model further down the VLM path, while the VLA task required it to branch off onto the action path. Yeah,
makes sense.
So that's all in the VLM4VLA paper.
That's great. So one thing that just came to mind, so did you guys try training from like a randomly initialized weights for one of the smaller VLMs?
Yeah, I think Jianke
like fine-tuning from a randomly initialized weights, I guess. I'm just curious, it would be interesting if it turned out the answer was it doesn't help at all. I can't imagine that's the case, but it'd be, does that make sense?
There's an ablation study in the paper. I think Jianke initialized from random weights, and it performs really bad.
Yeah.
I
Okay.
think.
That's good.
Yeah,
The
I showed that in the
comments.
paper and not.
Not here. That's fine. Yeah. Makes sense.
Yeah. From training from scratch really gets a very low performance. Like
Yeah.
on Kelvin, it drops from 4 to the 1. Yeah. Like
Yeah.
this kind of degradation.
Yeah, makes sense. Great. So yeah, well thanks. This was a really, really interesting discussion. I really like this kind of work where you just like aren't trying to like come up with some new algorithm or anything, but are just trying to understand like the behavior of these systems that we all use all the time. So I thought it was a really, really great discussion. Jeff, did you have any final questions? Otherwise we can do our wrap up question.
No, I don't have. I think as well.
We asked tons already.
Yeah. I mean, I already asked a ton of questions, and maybe if one day you can do that pre-training, that'll be quite exciting.
Yeah, it would be very, very interesting to see.
Actually, I think the need for the next step is to do this kind of large evaluation in the real world.
Yeah, that would be. I'm always very curious as to how well any of these findings hold up from these benchmarks to the real world. And the answer is okay. Yeah, very cool and very interested to see. I guess. Yeah. Okay. So, final question that we always ask everybody: do you have any cool papers that you've seen, or results, or demos, or anything that you've seen lately that you'd like to give a shout out to?
Okay. I think I want first shout out to the physical intelligence, since they really make this VLM-based VLA shine. And also recently there are many papers based on video prediction models, which I feel also very cool and maybe provide a very promising direction. Yeah, such as Cosmos Policy, Dream Zero, and also Mimic Video, and yeah, they are also all very recent papers. Yeah, and beyond the manipulation, I also want shout out for the Unitree, since they really show a lot impressive whole body control and locomotion demos on the public Chinese Spring Festival Gala. I think they almost killed the game. They finished the end of the game. Yeah, I really want to shout out for them. Yeah.
It was incredible. Yeah. Jianke, do you have anything?
Yeah, maybe I can mention some kind of paper like VLM4VLA, like doing some small research on the VLA itself. And I find I recently read a paper that explore how the different kind of co-training data influence the VLA performance. And like they discussed how like using the different kind of VQA data, using the latent action data, or using fast tokens action data, and they found I think their conclusions show that they think that the large VQA data co-training for the VLA can get a better generalization to the OOD thing in the real world, and I think that makes sense. And also they find something that's abnormal. Also, like they found that latent action or fast token, they did not get the similar effects on the OOD tasks.
Are you talking about the large behavior model paper from
TI? From LBM.
All right. Yeah, that's great. We'll have to check that out. All right. Yeah, great paper. Yeah, thank you guys. Thank you guys for coming on. Thank you for discussing your work. It's really interesting stuff. Good luck with the future projects, and we'll have to see what comes out of it. Bye.
Thank you for having us. Thank you, Chris. Thank you, Zhang.